Hello. What we're going to do in this video is practice one of the trickier exam questions to do with logarithms, where we're given some kind of experimental data, and we're given a suggestion for the model. So there's, in this case here, we've got some experimental data. X and Y are variables. Now, in the exam, they like to give them actual quantities, so X might represent, I don't know, concentration of some chemical, Y represents something else. To be honest, in terms of the exam, it's complete. It really doesn't matter what they represent. All we're worried about is the numbers. It's the physicist's job to decide whether the numbers are all correct and valid and everything. The mathematician's job is to perform the maths and do the calculations. So we've got some experimental data here. When X is 1, Y is 2, whatever X and Y are, couldn't give a monkeys, and so on and so forth. And the physicists, or in this case the exam, will say it's suspected that the relationship between Y and X is of the form Y is equal to A to the B to the power of X. Now notice here that Y, that's one of our variables, and X is the other variable. Okay, so we've got two variables here, Y in red and X, which is the power. Now here X is a power, okay, and our experience of dealing with things where the variable is a power tells us that logs is perhaps a good way forward if we're going to examine this relationship. Now I've got Excel up, and Excel can do some wonderful things. If I actually plot this graph, I get a scatter with a smooth line, and it's not going to do anything there because if we go there and select data, if I add the X values, okay, so I'm highlighted them, and the Y values, okay, you can see that it could be in the form of an exponential graph. It could be, okay. Remember, I've got get GeoGebra up here. You can bear with me 1 second. Let's have a view. Let me get the algebra bit up there. I get rid of that. Okay. Ignore all those bars there. But if we have y is equal to a to the power of x, okay, we can see here that by varying this, here is a typical exponential graph. This is the function y is equal to e to the 2x, and you can see there's similarities between that, okay, and the idea is, can we you can see there, yeah, exponential ends up off towards infinity. You can see there's similarities between the data. Got little dips there, but this is the experimental data we're after, we're dealing with here, and there'll always be some slight variation involved, okay. So I'm gonna leave that there for the minute as our motivation. Now, what they'll do in the exam, and what we need to do, because the x is a power, we need to take logs of both sides, okay? So we're going to take logs of both sides. So if we take log of that, we're just going to get, bear with me a bit, so if we take, we're going to get log of y. Now, I'm not worrying about my base. I'll put log there, so we've assumed that it's to base 10, okay? And we're going to get a log of all of that. Well, bear with me, I'm just going to make this nice and neat. AB to the power of x. Okay, so we take logs of both sides. That's our initial step. Then we're going to use our powers log laws to make this look a little bit nicer. Now, we've got two things multiplied together here. Now, be careful. We've got a multiplied by b to the x. Now, don't be fooled into thinking that a is also to the power of x and just automatically bring that x down to the front. It isn't the case. We'd need to have brackets if that was the case. So what we've got here is two things multiplied together, and when two things are multiplied together, the log of two things multiplied together becomes the two logs added together. Okay, so there's the log, and we're going to have b to the power of x. Okay, so there we have it, and finally, final step really, not a big step, now we can bring that power of x down, okay? So So there's b and the x, normal log laws. That x will go in the front there. Now, we don't know what a and b are. The physicist has given us the job of calculating what a and b are. I mean, we could estimate them from the graph we've got here, but we're a bit better than that. We want to be a bit more accurate, a more mathematical way. Now, what this represents, and I'll highlight that in, I'm going that colour. Looks nice. Looks nice. Right. I'm going to highlight that equation. What this equation is very similar to is actually the equation for a straight line. Y is equal to, now, let's decide which bit's which. The general equation of a straight line is y equals mx plus c, okay? And mx plus c, m represents the gradient, x is the variable, the x-axis, and log a is, c is the constant. Now here we've got an x, remember our variables, it's really important that you keep a track of what your variables are. We've got x as a variable, and we've got log y as a variable, okay? Now that means that our x, that's going to represent x in our equation of a straight line. Our log b is going to represent m. That means that log a is going to represent our y-intercept. So it's probably better off to write it as this, okay? And get that. No, it's not highlighting, it's being a little ripper. Okay, the x there represents the x, and here we've got log b is representing the gradient of this straight line. So you can add a shape on. So log b represents the gradient, and log a represents the y-intercept. Okay, if this was a straight line. Now, that means that we need to somehow plot a straight line. This isn't obviously a straight line. So if we look at our data, instead of plotting, at the minute we're plotting x against y. This is our graph for x against y. Now what we're going to do instead, look, now x is exactly as normal, okay? The x there and the x there. So we can keep our x values the same. But our y is now a log y on the left hand side if we're comparing it to a straight line graph. So I'm going to change this to log y, okay? I'm going to work out another column which is the log y column. So I'm going to take the log, and this will do it to base 10. You would do this with a calculator of all these numbers, and we get them like that, okay? Now they look a bit strange, so ideally you'd probably want to do them to, I'm doing here to 3 decimal places, because otherwise they look a bit strange, okay? So let's plot this graph now. So I'm just going to get rid of this, because I can, okay? Delete, done. Right, let's change the data. Select the data. So I'm going to add, my x values are going to stay the same, and, oh, no, I've made a mistake there, so this is the joys of Excel for you. X values there, and the y values there. Okay, now this is more of a straight line, okay? This, I mean, it's still got that little bump there, but that's, we've already said, experimental data. That's how it works. I don't know what that title's come about. Let's get rid of that. Don't know what that's about. Let's get rid of that. Okay, now, we need to approximate this with a line of best fit. Now, luckily, Excel can do this. You would do this by the eye. You'd roughly try and get as many points above the line as below. A lot of the time we don't need to worry about that, as I'll tell you in a second. So I'm going to add a trend line. It's linear, so let's do that. We're going to go, yes, that will do, close, and I'm going to go forward, I'm going to go backwards, -2, okay, that hasn't really worked out. Anyway, there's our straight line. There's our I'm going to format that to make it look a little bit bigger, because it looks a bit ridiculous at the minute. 2.5, that will do. Right, there's our straight line, okay? Now, we can use this straight line to find estimates for A and B now, okay? Now, we said that log B is our gradient, so we need to calculate the gradient of this line here. Now, luckily, we don't even have to worry about using the graph for this, because we've got the data which will tell us the gradient, okay? Now, remember, there's that text box here, that the gradient, in fact, we'll get an equation here, make it all nice and lovely jubbly, and that where is the equation? There it is. There's a little ripper. So we'll insert an equation. Remember, the gradient, the straight line, we can work it out by doing the change in y all over the change in x. Okay, so that's nice. Now, for the straight line, it makes sense to use the first and the last points for our approximation from the gradient. So we're going to be using these set of points here. Okay, so if we do that now, let's insert the equation again. We have as our approximation for our gradient. Now remember, our gradient is log b, so our approximation for log b, okay, is going to be equal to the change in y. Now the change in y is actually the change in log y. Okay, and actually I didn't want to highlight that. Apologies there. So no fill. Let's get that as no fill. It's these ones which we want to worry about, because that's the x values. So log b, the change in y, so in this case it's going to be 1.699 minus 0.301, and we're going to divide it by, lovely when it does it all like that for you, we're going to divide it by, in this case, 5 minus 4, the change in x. This shouldn't be too bad of a problem to calculate, so let's just do this. I'm going to put the log b there. Okay, I'm going to do it here. So the gradient is going to be, you would do this on paper, changing that minus that, divided by these mega brackets in Excel. If you're clear with your workings, you won't have to worry so much. So we're looking at 0.349. Okay, so log b is 0.349. Okay, we'll go to 3 decimal places because I've got limited at 3 decimal places. Now, we don't want log b, we want to find b, so we need to undo the effect of that log. Okay, so to undo the effect of that log, we are going to, well, it's log to the base 10, so b is going to be equal to 10 to the power of 0.349. And again, I'm going to use Excel to calculate that. So let's get that, enter, lovely old job. So it's going to be equal to, and I'll just use Excel there, to 10 to the power of 0.349. So our b, and to two decimal places there. Let's have a look. Let's insert the equation there. Oh no, we're already there. I don't know what I'm doing really. B is equal to, well, we've dealt with 3 decimal places before. It makes sense to keep it there. So as that 2.234. Okay, that's our approximation for B. So we've calculated B in our original thing there. That's brilliant. We're halfway there. Now we've got to calculate A. Now log A represents the y-intercept. Now this is where you're gonna. It's even more of an approximation really, because unfortunately Excel can't be bothered to faff around. But if we look there, if this line's best fit continued, it would approximately go there. Now we've got to make a hell of an approximation for that. Well, I would say it's a quarter of the way between 0.2 and 0.0 and 0.2. So a quarter of that, a quarter and fifth is a 20th, which is 0.05. So our y-intercept, which of course in this case is log A, we can approximate that as 0.05. Okay, a 20th there. Get rid of all that because we don't need it. So the next step would be to it's quite simple here. We don't have to do as many calculations. A is going to be 10 to the power of 0.05. It's going to be a tiny number, but that's the nature of maths, I guess. You know, I don't want to be too discriminatory against small numbers. They can't help it. So that's so putting 10 to the power of 0.05 there, we get a value of A as being 1.2. Value of A being 1.22. Okay. So, oh, sorry, I made a mistake there. 1.22. So what this means, well, I'm going to just put it there. We have found the values of A and B. We've done the job for the physicists. They're happy. we're happy because we've just done a cheeky little bit of maths. So the equation is actually going to be y is equal to, well, it's a 1.122 multiplied. Now you have to be a bit careful here because with letters you don't have to have, but be a bit careful there. And b is 2.34 to the power of x. Okay, and that is our approximation for what the equation of the curve is for the original x and y involved. Okay, so we've used logs and a bit of knowledge about straight line graphs to figure out what those numbers were, if that is right. Now, just to show you that this isn't just a bit of hocus pocus, I'm gonna make my y's again, but this time I'm gonna use this formula. Okay, so y is equal to 1.2122 times by 2.34 to the power of x. Okay, so there we go, and you can see that value came up as 2.6. Then we get 6 when it should have been a 7. Let's see how it works. 14 instead of 11. 33 instead of a 23, right? We're losing a bit of accuracy here. 78 in terms of a 50. So that wasn't massively accurate. There was going to be some rounding errors involved here, but the principle is sound. It could be that maybe this wasn't as good a straight line as we'd thought, in which case we could say that this wasn't a suitable model. But that's beyond the kind of scope of what we're supposed to be doing here. So that's one example when the model is when one of the variables is a power. That's one of the models. Let's have a look at another one. Here's another set of data, but the physicists propose something different here. This time they propose that it's y is equal to a x to the power of something. Now notice here that the variables this time, y is in the same place, but x is now the base. It isn't the exponent. Okay, so let's see what happens here. Now we're still going to take logs of both sides. Let's make that. Okay, what did I do last time? I copied and pasted. Okay, so copy and paste. Let's take logs of both sides here to see what happens in this case. Slightly different model because x isn't the power anymore. So log, I can't read what's it. Oh, it does it nice for me. Lovely old job. Right, so log, taking logs of both sides, standard. Okay, this bit is the standard part of the exam. You should all be trying to get these marks. Now, I've got the two. Let's get that. So log. Okay. Oh, that's nice. I wasn't. Oh, what the hell has happened there? It's all disappeared. Control Z. Control Z. Right. Brilliant. Whoa, it's disappeared again. You got to love a bit of office, haven't you? Right. Let's move that. Right. You're happy now, right? No, not happy apparently. Right, what the hell's happened here? Right, let's just get rid of that. That is what's causing the problems. Right. Get there in the end. Log x to the power of b. Right, brilliant. Done. Now we can bring the power down. And someone is to muck up again, otherwise I'm going to get a bit mad. Right, good. So let's compare this to y equals mx plus c this time. So I'm just going to get that up there. That'll save me a bit of typing. Right, let's compare this to y equals mx plus c. Now this one's a bit different, so let's just change the color of that. Okay, let's see what the comparison is now. Now this bit is different. Okay, before we had an x, and an x was just outside the log. Okay, so we kept that as normal. Now the x is a log x, so that's going to make things different. That means the gradient is b. Okay, the y-intercept stays the same. Okay, so log a is going to be c, log x is the new x, log y is the new y, but b, the gradient, is going to be b. Now that simplifies things slightly when it comes to the graphs. I'll show you, because now instead of plotting x against log y, we're going to plot log x against log y, because the x appears in the log. So let's get log x and log y. Okay, so if I just take the log to base 10 and I do it to that. Now the beauty of Excel is it's just going to go like that, and I'm just going to go bosh, like that. Brilliant. Brilliant. I am happy as Larry. I don't know why. Yeah, okay. So, now we're going to plot these values. So if I insert another scatter graph, and what the hell has happened there, we do not know. When Excel does this, select data, I'm just going to remove all that because I don't know what is going on there. Happy. Right, X values and my new log values, done. My Y values are there, my new Y values, done. Oh, that looks a lovely straight line. Brilliant. Okay, now this is going to be a bit more straightforward, I think. So let's do what we did before. Now the gradient is B. Now again, if we deal with that, what I'll do is I'll just take this really, because just putting in new numbers, exactly the same method. Putting in some new numbers. Let's put that there. So the gradient is going to be, well, it's change in y, which is log y now, divided by the change in x. So our gradient, why did I do that? Numpty. Right, so 2.585 minus 0.301. Okay, so that's the change in y. Change in x this time is going to be a bit. It's going to be a bit more of a nightmare to get easy. You're going to make mistakes with calculation errors here because there's a lot of numbers to put in. So change in x 0.7, 3 decimal places, 0.700 minus 0. Okay. So our gradient, and I'll put that as log b, and that's wrong of me because it's actually just b. We don't have to undo the b here, so that's quite nice. So we'll just do that as equaling. So this is what you type into your calculator, divided by, well, 0.7 effectively. So 3.263. So that's great. We've got b straight off the bat. Okay, 2.263. It's actually very similar. Or 3.263. Excellent. Now, our y-intercept. Now, this is a lot nicer because, look, we know where it intercepts. When log x is 0, log y is 0.301. So that's telling us that the y-intercept, if I just copy and paste it from there, the log intercept, in this case, log a, is going to be 0.301. Okay, which means a is going to be equal to, let's get rid of that because that was from the previous question. I'm just being lazy. 10 to the 0.31. So let's just do some calculations there in that random box. 0.301, and it's 2, which, okay, so a is equal to 2. So that means we've got our model. We've got our model. Okay, a is going to be 2. Remember, it's a times x to the power of b. Okay, and in this case, we can get rid of all these because we've got some variables, so it'll be x to the power of, and our value, whatever our value of b was, and our value of b was 3.236. Okay, so there's our model. We've done it. We've found out what a and b is. Now, just to compare again, we may as well. If we compare it, so it's going to be 2 times x. Oh, let's just get x to the power of 3.236. Okay, so 2. Just what we wanted. Okay. Oh, 18, 69. It's losing its accuracy. 177. It's that got better. It's in the ballpark figure. Okay. But again, it's not our job. That's the physicist's job. Our job is to get the values. Okay. Now these questions will usually come up as a section B question. There's a lot of easy marks here. There's a lot of easy marks if you just remember the method. The trickiest thing is deciding what you plot. And you've got to look at the variable. That's why it's key to look at what the variables were. Here we plotted log x and log y because both our variables, when we did logs of both sides, they became part of the log. In the previous question, we plotted x against log y because it was only log y which was being logged, and that's fundamental to how you do this. I hope that's helped. I'm now going to have a cup of coffee and make my dinner.